Welcome to Physics 142 Online again. This is one of the example problems that's in your textbook but is not completely solved, although the answer is given there for reference. So I wanted to work it out and take you through the steps of a little bit more complicated problem where we use Coulomb's law and a little bit of calculus to find the electric field of a continuous distribution of charge. So here's the problem. Find the electric field of a uniformly charged non-conducting ring of total charge Q and radius capital R on the axis, a distance z away from its center. And so you can see in the sketch all of those elements are shown. Also, what we want to do is to break the rod down into little elements of length dl, and this is suggested in the textbook as well. So we'll call that little piece at the bottom of the ring a piece of the ring, and we'll call its length dl. It's a differential distance. Also, in order to write down the various components of the electric field vector, we're going to have to put an angle theta in, and a little bit of geometry can convince us that the angle theta here and the angle theta here are the same. And also, we're going to have to put into the diagram a variable that labels the distance from the point on the axis and the charge element dl. So of course, dl is the length, dq is the charge element in this problem. dq is the amount of charge on that little piece of the ring of length dl, and that's pretty easy to see how those two are related, because dq is the total charge. The charge per unit length, we can calculate charge per length. We get that from knowing the total charge of the ring and the circumference of the ring. So we're going to take that quantity and multiply it by the length element dl, and then we'll have an expression for dq when we have to put that into the integral. So charge per unit length is q over the circumference 2 pi r, and the length element is dl. So we have a simple relationship for dq when we need to use it. dE, which is the differential amount of electric field at the point P on the axis due to the charge element dq at the piece of the ring dl, dE is just k dq over r squared. Okay, so in just a moment we'll be able to set up the integrals that are necessary to do this problem. But remember, the electric field, of course, is a vector, and so being a vector, we have to work out the different components. And it's pretty clear here that for the little piece dl, there will clearly be a z component of this electric field, and I'll write that over here. dEz, the z component will just be the magnitude of the vector dE times, in this case, right, the cosine of theta. Cosine of theta gives the horizontal component, or the z component, and cosine theta, we can express that very easily using the right triangle that is part of the ring. There's a right triangle there. Cosine theta will be the radius divided by the distance little r. Alright, so let's go ahead and make some substitutions here. dE, we know, is k dq over r squared. Cos theta, we just said, oh, I had that wrong. Cos theta is z divided by the distance r. Right, so I caught myself in time for that. Z over capital R, that's cosine theta, over small r is cosine theta. And now dq, we'll be able to substitute that in here as well. So we get k dq now is q, and then we have a z here and a dl, and everything that's in the denominator will involve 2 pi times the radius times the distance r cubed. Now r, of course, is related to z and capital R through the Pythagorean theorem, right? So if I just go one more line here, k q z dl over 2 pi r, and r itself is the square root of capital R squared plus little r squared, plus z squared, and when we cube it, see if this makes sense to you, we get capital R squared plus z squared to the 3/2 power, because little r itself was capital R squared plus z squared to the 1/2 power, and then we're cubing it. So now we have that expression for dEz. That's what this is. And that means we ought to be able to find the z component of the electric field by simply integrating this all the way around the ring, so as to take into account the contributions of all of the length elements dl all the way around the circumference of the ring. But before we do that, first let's think about the y component and the x component of the electric field. And in the sketch in the book, the y-axis is upward, and so that makes the x-axis, no, I'm sorry, the x-axis is upward. So I'll just erase that, replace that with x. The x-axis is upward, and that must mean the y-axis then is coming out of the board or out of the page toward us. You can see that there will be an x component to the dE vector, and that would be given by dE sine theta, right? But let's think about that just a little bit. So the EX will simply be the integral of dEx, integrated all the way around the ring. But the reason the sketch is drawn the way it is to show that if we look at the contribution from the length element dl at the bottom of the ring, we can compare it to the contribution for the length element dl at the top of the ring, up here. And look what happens. Those two dE vectors, they both have the same z component, because they both lie along the positive z direction. But if the x-axis is upward, then the dE on top of the axis up here has a positive x component, whereas the dE lying in this direction has a negative x component. And I can take the entire ring and pair up pieces on opposite sides of the ring that have the property that their x component of electric fields will cancel each other. And so what we can see if we integrate all the way around the ring is that this is going to be equal to 0 by symmetry. And symmetry is one of the really powerful arguments that we can use in physics, rather than do all the work to perform that integral and find out when we're all done with it that we get 0. Sometimes we can tell the answer before we even work out the calculation. And that's the case here. Also, the same kind of reasoning would apply to the y component of the electric field, because it's hard to see it in the diagram the way it is, but if the length element were not exactly at the bottom of the ring, but were up along one of the sides of it, then there would be a y component of the electric field as well. But again, if we integrate all the way around the ring, then we would find that all of the y components of electric field would cancel out by symmetry as well. And once again, we would know that because we could take pieces of the ring, these length elements, at opposite sides all the way around the ring, and they would give components in the y direction for their electric fields that would always be opposite one another. So these two facts are very powerful and simplify the calculation that we might otherwise have to do. So all that we need to do now is perform the integral for the z component, because we know this one does not give us 0. look at the sketch again. If that's not clear, the reason this one doesn't give 0 is that the dE vectors for the length elements at the top and the bottom of the ring, and you can make the same argument for pieces on opposite sides of the ring, all the way around, they will always have electric field, differential electric field vectors that have positive z components, right? So the dEz, what I can write is that all the dL contributions that are part of that integral are positive. In other words, they give z components to the electric field that are all in the positive z direction. So when we do this integral, we can take the pieces of it, the integrand, which is right up here in this fraction, we can take the terms that are constants and bring them outside the integral. So that includes, of course, the Coulomb constant K, the charge Q, which is the total charge of the ring, that comes out in front. Z, well, as we integrate all the way around the ring, Z doesn't change, so that comes out in front as well. Right? And what about the denominator? Look at the denominator. 2 pi, that's obviously a constant. The radius of the ring is a constant. And look at the r squared plus z squared term. Those are also constants. They're not affected by performing the integral. So all of those terms, as we integrate around the ring and add up all of the contributions of the different length elements, all we end up with, it's inside the integral, is dl. And what that means is dl is this differential length of the ring. So what the meaning of that integral is the sum of the length elements all the way around the ring. And that should be pretty obvious what the answer is, because that just means we add up dl1, dl2, dl3, and as we add them up all the way around the ring, what we've done is we've added up lengths that add up to the circumference of the ring, right? Just 2 pi times r. And so we actually don't even have an integral to do. The integral is simply adding up pieces all the way around the ring, and we know what their sum has to be because they're adding up to the circumference. So let me take the result for E sub z to make this a little less crowded. Let's put this over here. We get K, Q, Z times, now from the integral we get 2 pi r. The denominator, hey, the denominator has 2 pi r in it, so that's going to cancel out completely. And then we have capital R squared plus z squared to the 3 halves. So the 2 pi r terms drop out, and we end up with, for the z component, kqz over capital R squared plus z squared quantity to the 3 halves power. And one last thing, if we just want to write this as a vector, then we would say that E is equal to this E sub z in the k hat direction. So it's a little bit tedious, but just to make sure that you see exactly how the answer ought to be reported as a vector quantity, we write it down like this. And now what can we do? Can we test this answer? Because in class I've talked about checking your answer to see if it makes sense. First, let's check the units. Okay, the units of this are, the units of E are always the Coulomb constant times a charge divided by a length squared. And in this case we've got the K, right? We've got the Q, and we have a length in the numerator divided by a length squared to the 3 halves, or a length cubed in the denominator. So here we'll write it as KQ, of course the units associated with those quantities, times a length in the numerator, that's the Z. In the denominator we have a length cubed. And so a length over a length cubed is 1 over a length squared, and that gives us the right units. The sign makes sense because we know from the sketch that the electric field vector ought to lie in the positive z direction. Oh, and of course, I forgot to put in k hat. So I should always put the unit vector in my expression for a vector quantity. And the last thing we can do is check the limiting case, because the sign works out, the units work out. What's the appropriate limiting case? That's easy, right? The limiting case that we want is, what if the point P gets really far away from the ring? So in other words, the coordinate z gets large compared to the size of the ring. Limiting case, z much, much greater than r. And if we look at the expression, the exact expression here, that means that in that expression, the denominator term, r squared plus z squared, if z is much greater than r, that will be approximately the same as z squared. And if we plug that in, right, then that means our approximate E will now be, in this limiting case, k q z over the denominator. That's going to have z squared to the 3 halves. And so, of course, that's in the k hat direction. What will that give us? Z squared to the 3 halves is z cubed. K q over z squared is the final answer in the k hat direction. And sure enough, that looks just like the electric field due to a point charge q. Remember, q is the total charge on the ring. That was in the problem statement. So if we get really far away from this ring of charge, it behaves. It has the same field that a point charge would have at the same distance. So we recover the formula for the electric field of a point charge, and that's exactly what we would expect. So we've checked the units, we've checked the sign, and we've checked the limiting case, and we feel really good about the agreement here. Those kinds of checks, of course, won't be able to tell us whether we might have a numerical factor in here. Maybe I threw away a factor of 2 without realizing it. That wouldn't be picked up by any of these tests. But really, gross errors, algebraic errors, if I mixed up the power of a particular coordinate, those kinds of errors would be caught by performing these checks. So it's always a good idea. So here's the final answer for this case. And this problem was one where, of course, we had to use calculus to set up the problem. But once we did, the actual integral that we got over here was so simple that it didn't really require any calculus knowledge at all. So sometimes we will get lucky and have problems like that. In the meantime, work on these homework problems, work on getting them set up, going through the steps that I indicated in class to set these things up. And in this problem, we're introduced to the powerful use of symmetry in simplifying what would otherwise be a much more complicated problem. So think about that and make sure that you understand the logic behind those statements. I'll see you in class.